Okay, now recording is started. So welcome all and good afternoon to our today's graduate seminar. I'm Adnan Kefal from Sabancı University, working as an assistant professor for Faculty of Engineering and Natural Science and serving for the Committee of FANS for Industrial Engineering and Manufacturing Engineering programs. Today, our guest speaker is Francesco dell'Isola from University of dell'Isola, I think, the International Research Center for Mathematics, Mechanics of Complex Systems, M&MoCS, Italy. I would like to thank him again for participating in this graduate seminar and to give us a talk on his research study on the synthesis of metamaterials, new material and theoretical challenges. This seminar is planned for 50 minutes, including like 40 or 45 minutes of presentation time, 10 to 15 minutes of question and answers time. So let me quickly go through his short biography. Francesco dell'Isola has a laureate in theoretical physics and a PhD in mathematical physics obtained at the University di Napoli Federico II. It was a professor at the University of Aix-Marseille, Rome La Sapienza, Toulon, Virginia Tech, California, Berkeley, Lobachevsky de Naya Novgorod. His work were dedicated to the synthesis and numerical experimental study of novel metamaterials, either based on microarchitecture structures or exploring the piezoelectric coupling. He also studied the applications of discrete Lagrangian models, their homogenization, and the formulation of the corresponding higher gradient continuum models. In doing so, he was obliged to attentively examine the original sources where the mechanics of continuous media were formulated at first. And thank you very much again, Professor dell'Isola, and stage is yours.
Okay. Thanks a lot for the invitation. I had very positive experiences with Turkish scientists with whom I am collaborating intensively. Of course, I met Erdem Yıldızdag in Berkeley, but I understood immediately he was from the Mediterranean Sea. We are working together systematically. Okay, the list of co-workers with whom I developed the ideas which I will present you is here. It is partial. Let us start immediately specifying what we mean with the word synthesis. Okay. Usually, when you study a physical phenomenon, you have a phenomenon and then you look for mathematical formulas describing the phenomenon. So your mathematical model tries to predict what the system, the physical system will do. Okay. Now, in the synthesis problem, we have the opposite. You write the equations, and then you look for a physical system whose evolution is described by your equations. Okay. Is this completely new in metamaterial theory? Because you know a metamaterial is a material having exotic properties. I will go to this point in greater detail later. Okay, this is not new. Why? Because in the theory of analog computers, the computers which were used before digital computers, the problem was exactly the synthesis of electric circuits governed by a given equation. You wanted to study a structure, a bridge, a three-dimensional continuum which is being deformed. Then, as you could not calculate the solutions with analytical methods, and you wanted a simulation describing you the solutions of that problem, then you were looking for an analog circuit like this one, which I'm showing you here, which is the analog of a Kirchhoff plate element, then measuring, for instance, the, I don't know if you see the hand of my mouse.
We can see that.
Okay, so you go here, you measure the potential drop there, and then here you have an estimate of the partial differential derivative along x of the displacement, which is the analog of the potential energy. So this was a way for getting some interesting predictions using complex mathematical methods. By the way, I recently applied to vibration control via piezoelectric transducers the concept of analog circuits. Okay. Then I will only talk about one specific equation, which is this one. I don't know if you see it fully. Okay. This is a deformation energy. So F is the gradient of placement. We are talking about a plate, okay? And you have two directions, the direction of this beam, which is D1, and the direction of that beam, which is D2. And this is an energy which we want to synthesize. So given this energy, we want to find a microstructure which, once homogenized, gives you this macro deformation energy. So mathematically speaking, you have shear, which is given by this term, which is the measure of the deformation energy related to this change of angle you see here. Then you have elongation, the elongation of one of these or the other beam, and it is represented by this term in the energy. After homogenization, I mean, when you have many elements of these which are reproduced in your system. And this is the bending term, which involves the gradient of capital F, therefore the second gradient of placement. So even if the technical details are not very important in this context, what I did, giving this energy, I have found a microstructure which, once homogenized, gives you this deformation energy. Why I liked this energy very much? Because I wanted to synthesize a material, so find a microstructure for a material which elongates with zero or very low deformation energy. So my problem was, I want a material which increases its length a lot and remains in the elastic regime, and there are low deformation energies involved in this elongation. So this is one synthesis problem which I could manage to study. Look, this is the Pandographic structure made of flexible beams, and I used this microstructure for getting another interesting object, which is what is described in this C. This is the microstructure. If the we zoom in this upper beam, we find this microstructure, and this is a very unusual beam. This beam can change its curvature if it is uniform without energy. So the deformation energy of this beam depends on the third derivative of displacement, which is a rather exotic metamaterial. Okay. So I could also invent a material like this one, which is made of two families of orthogonal Pandographic beams, and these deformations which you see here, they are all with zero energy if the pivots are perfect. So you have a material which deforms in an homogeneous way in the plane without any deformation energy, which is what we want, because when you introduce a very small deformation energy related to the angle change in a pantograph, then you get a material which I can call this a bipantographic sheet. And this bipantographic sheet has a deformation in the plane, homogeneous deformation, if the pivots are perfect, which are totally energy free. So in a sense, they are what mechanical engineers call a machine, because you have degrees of freedom and the system is changing without a lot of deformation energy from one configuration to another among the allowed ones. Once you homogenize this material and you add a small deformation energy related to the shear deformation, then this becomes something which can be used in large deformation, remaining elastic in large deformations. Are these dreams only dreams, or they can be transformed into real life objects? Okay, we printed this structure. If you see, we tried to get perfect pivots in this specimen as quasi-perfect pivots. And this material is made of two families of mutually orthogonal beams in the reference configuration. They are intersecting by means of some cylinders, which we call pivots. Perfect pivots have no torsional energy, so there is no shear macroscopic energy when you deform this sheet. In the bias extension test, the first stage of elongation of the structure corresponds to bending of the fibers, which in a continuum model is represented by a second gradient energy, which is rather unusual. In the deformation energy, you have a second gradient of displacement, which is rather rare in the literature. Why all this is happening? Because the homogenized model corresponding to the pandographic sheet has a deformation energy, which is either second gradient or extensional. Okay, so either you have an energy related to the second derivatives, bending of beams, or you have an elongation of a bar constituting the system. Okay, a pandographic beam by itself is designed and printed in 3D printing machines rather easily, and you see that this is the shear deformation of this beam. And it remains, this picture has been made in Berlin, and the dots are needed for following in the digital image correlation the displacement of this structure. By the way, it is rather difficult to teach to a software how to follow a mechanical system which is deformed in large deformations. And we need it with a very sophisticated digital image correlation system, which I will describe you later. Okay, unfortunately, I have not the movie because I'm using a computer which is not mine. However, I can tell you what happens. This, with words, this beam behaves in a range of displacements like a beam. When you reach a threshold, it becomes a cable. So you have a kind of phase transition. When these two beams here, constituting the typical element of our structure, become parallel, then it becomes like a cable, because here you have pivots which are perfect at the top and at the bottom. So you have small segments which are articulated like a catenary in a sense. So this metamaterial has a mechanical phase transition inside. However, many persons, when I described what we are doing, criticized our conception, because they said, okay, can you print perfect pivots? Now, the answer is yes, we can do this. And this is the 3D picture of the CAD file which we have used. And you can see here that this is exactly an internal cylinder. You have an external cave cylinder, and the internal cylinder is connecting the top bar and the bottom bar for getting a system of perfect cylinders, those typical of standard mechanical engineering. And we could print the specimen, which is, this is the picture of the specimen, and we could prove experimentally that the behavior which I described to you before, this one, so with this kind of deformation energies, which are very associated with a very low deformation energy, are feasible experimentally. So this material, this Pandographic sheet, can undergo large deformations remaining in the elastic regime. It starts being broken when one of these pivots undergoes a strong shear deformation and it breaks. The dream is, I mean, this is a big cell. The dream is to be able to build these metamaterials with small cells. So the idea is to build a kind of tissue based on this microstructure. Okay. So, and this was made when I was in Berkeley, where I met Erden. We started printing millimetric Pandographic structures, which have been tested and fully studied in Kansas University, where Anil Misra, Professor Misra, is working. And what we discovered, that the Pandographic structure has a peculiar feature. Its mechanical behavior depends on the mechanical behavior of this small pivot. When you change the diameter and the height of this pivot, then the overall macroscopic behavior of the system changes dramatically. Actually, for a fixed height, we could prove both theoretically and experimentally that the torsional stiffness, so the shear stiffness at macro level in this figure here, you see the change of angle from here to there. So you have a shear deformation at macro level associated to a torsional deformation of this pivot. Okay. We have proven that it goes with the fourth power of the diameter of this pivot. So a very small change of this diameter causes a large macroscopic change of mechanical behavior. This is also proven experimentally with pivots of different types. You know, we have A1, A2, A3, A4, B1, B2. They are pivots. Here are the dimensions of the pivot in the millimetric structure, this one, okay? When you impose this displacement here and you plot the force as a function of the displacement, what you get? you get that for displacement 1 millimeter, you get this force. 2 millimeters, you get that force, and so on. So you have the dependence displacement force, okay, and what you see with B2 specimens, so with specimen having this B2 dimension, you get a maximum of the exerted force. And you can range from 0.25 up to 2.25, simply changing the parameters characterizing the microstructure. So what it means that with a very small change of volume, so changing a little bit the diameter of these pivots, you can get a macrostructure whose mechanical behavior is dramatically different. Then we superimposed several layers of pandographic structures, and we have found that in a 3-point bending test, superimposed layers of pandographic structures have this very peculiar behavior. By the way, this deformation is fully elastic. If this moves up, the pandographic structure goes back to its original shape. And this effect can be very useful, for instance, in every damping device. And with Erden, we are trying to exploit this effect in a specific problem in mechanical engineering. So the question is, the technological bottleneck is how to design and print perfect pivots. As I already told you, perfect pivots seems to be very important. Indeed, they are. But many persons were skeptical about our capacity of using 3D printers, leaving here, of course, in this drawing, it is exaggerated, leaving here the space, allowing for the relative rotation of this beam with respect to that beam. Okay. What happened is that we managed to do this. We did it in Warsaw, and using a Formiga 100S printed, we could get specimens in which, without doing anything else than 3D printing, there are parts inside the printed object which move one with respect to the other. This fabrication process up to now has been successful only with plastic pivots. With metallic pivot, this design is not working. However, recently I started a collaboration with Fraunhofer Institute in Freiburg, and they are able, changing this design, inventing a new design, to have a 3D printed structure in which metallic parts are moving one with respect to the other. Okay. So in the additive manufacturing of metallic specimens, we are having serious troubles. You see, this is a specimen after printing. They need to be thermally cured for becoming straight, and it can be very difficult. But at the end, at the Fraunhofer Institute, they did manage to get straight specimens. However, we discovered, this is a microscope picture, we discovered that these pivots are not rotating, and they are broken after deformation in this way. So we needed to develop a better design. So this is a rather difficult problem in mechanical engineering for getting perfect pivots, which at the end could be printed also in metal. Even if I don't have here pictures, we did not publish yet the papers, and my co-authors did not allow me to show you the design. If you zoom at different length scales, the specimens we are considering, at this length scale, you can use the model beams. If you zoom in and you go there, you can use only the model three-dimensional continuum, which, by the way, if you look at the grain size, is rather inhomogeneous, okay? Okay, we'll come back to this point later. And as I told you, when being in Berkeley, we decided that we wanted to do better. And Zacharias Vangelatos, who is now working in a company, so he left academia, had the clever idea of printing these specimens, which are 20 micrometers. And these specimens have been tested. And we could prove that what happens for millimetric, centimetric, millimetric pandographs still occurs in micrometric pandographs. So what we are studying is not the specific material or a phenomenon which occurs at a specific length scale. We are studying the mechanical behavior of a microstructure. Okay, and this is very important for what we are telling. This is confirmed by a casual circumstance. Okay, two colleagues from Germany, the family Hesch, they are husband and wife from University of Siegen, Christian, I'm sorry, I forgot the name of his wife. They studied this tissue. You see, this is a standard tissue made of carbon fiber, and this is embedded in a matrix of a polymer. And they repeated the bias test. Now, this region, the warp and the weft here, so the fact that the fiber goes down and goes up and the other fiber goes up, here it is produced a kind of pivot. And actually, this material behaves like a pandograph. It has a pandographic-like response. Okay, so this is a property of materials having a certain microstructure. So whatever is the lower scale material you are using, aluminum, nickel, polymers of every kind, or carbon fibers, the dominating, at macro level, the dominating mechanical effects are dictated by the pandographic microstructure. Okay, and this is a small, how to say, theoretical discussion which we are trying to develop. The theoretical discussion is about homogenization. If you use this wide knit pandographic structure, this intermediate knit and this dense knit pandograph, you discover that at macro level, the behavior of all these three is the same. And this is rather, how to say, unexpected. We should find theoretically the reasons for which this is true, okay? All these three structures behave governed by the pivots properties and the bending stiffness of involved beams. However, here you have a very nice phase transition. When beams touch one with the other, then in the center of this material, you get a standard three-dimensional continuum, exactly as those which we are studying and teaching for our students. So you have a kind of second gradient material, which after a big elongation becomes a first gradient material. If the mechanical properties and the geometrical properties of the considered architectures are well optimized, then your material remains in the elastic regime when it arrives at this level, okay? So that you have a material which for certain displacements behaves like a second gradient material, so large elongations are allowed, and when you reach a given threshold, it stops behaving like a second gradient material and starts behaving as a standard one. Okay, what is happening? I'm not writing equations, but I'm telling you the interpretation of our results. When you have a pandographic microstructure like that, without lateral constraints, it elongates if the pivots are perfect in this way. So you have that from here to there, you go without deformation energy. If you block the distance between these beams and you elongate, then the bending of the beams become dominant in the deformation pattern, and everybody knows that in the deformation of a beam, second derivatives of displacement occur, and at macro level, after homogenization, you get a second gradient continuum. Okay, so this was the idea of the synthesis. Of course, this material is broken. Okay, so I will tell you for an elastic, for a metallic specimen, this is the plot of deformation, the pictures of the deformation. Look, you have a large deformation in the elastic regime before rupture starts occurring. So this plot shows you in a clear way that our idea of synthesis of metamaterials, this idea is rather well-grounded, because you have at the beginning linear elastic behavior. Then you have nonlinear elastic behavior, okay? Then somewhere here, you have a beginning of plastic phenomena, damage occurring somewhere in the structure. And then you have this very nice pattern. This is displacement, exerted force in the bias test, okay? Consider that at the maximum, this specimen, which is 3 centimeters times 9 centimeters, can exert 0.8 kilonewton, a lot, okay? And consider that a specimen which is long 9 centimeters can elongate 25 centimeters, 25 millimeters before going out of the elastic regime. Okay, what happens here in this point? A first pivot is broken. Okay, then you have a sequence of ruptures when other pivots are broken without failure. So this means if you calculate the area under this plot, you have under this region the energy which is needed for arriving at the total failure of your specimen, and the area under this plot here, say until 25 millimeters, is the area of the energy which can be engaged in the elastic deformation phenomena. So you can consider it the amount of energy which the material can store working without being damaged. So what you have, that the amount of failure energy is equivalent to the amount of elastic energy. This means that this material which we are going to invent is indeed resilient. It is resisting to damage phenomena in a very effective way. Okay, then when we made experiments with so-called quasi-perfect pivots, are pivots which are nearly perfect, okay, but they are not printed as they should be. Okay, in red, you see the plot of the numerical simulations forecasting the behavior of a perfect Pandographic sheet, and in blue, you find the experiment. So you see that more or less, we are going towards the desired behavior in our experiment. And this is the experimental plot also after rupture, when you have the famous phase transition I was talking about. So the beams are touching one with the other so that you have a stiffening of your material. So you have a kind of material which has a stiffness in a certain deformation regime, another much higher stiffness in another deformation regime. If we manage to design pivots and the structure in an optimal way, and I have partial results in these aspects, then we will have invented the two-phase material which we are looking for. First phase, second gradient, second phase, first gradient material. Now, somebody told us that this specimen is behaving very well, but it is useless because it could buckle, it could not resist in shear. So we developed shear tests, again in Berlin, and this is a very nice pattern of deformation. As you can see, this specimen still behaves as a second gradient material also in shear deformation. The only problem is that sometimes this material buckles, okay? So it gets out of the plane of deformation, but in a way which is not catastrophic, and by the way, totally described mathematically. These specimens are damage tolerant. This is a specimen which, for a reason which we could not understand, has been printed with some small defects, okay? So while testing it, we had some jumps in the plot displacement overall force. By the way, we are talking about 100, 200 newtons. So it is rather stiff for being such a weight, light, so not heavy specimen, okay? So what happens? One beam is broken, but it keeps doing its job. Okay, so we are optimistic that this microstructure produces a damage-tolerant metamaterial. Now, let me tell that the energy which I gave you before is rather successful, because thanks to it, we could get these numerical simulations on the right. You see the superposition of the picture we had making the measurements, and the colors are the deformation energies. So we know exactly where are the parts of the structure which undergo the highest deformation energy. We knew that it is here that you have this concentration, and experimentally, we have seen that it is exactly here that the specimen was broken. So we have a theory which allows us to design these experiments in the best possible way. I hope that you allow me 2 minutes of philosophical considerations, only 2 minutes. Without a theory, you cannot design experiments. We could design this metamaterial simply because we had a very careful mathematical model and very good numerical simulations, which allowed us to forecast the behavior of the specimens which we were going to build. Of course, if in the building you have defects, then you get a different behavior, okay? It is rather difficult to get such a well-ordered microstructure, but actually we are succeeding in this. Okay, then we discovered that there are other damage patterns. So for instance, look, this pivot inside is broken. So we discovered that our mathematical model, the one which has directed us in this part of experiment, was not efficient enough. So we were obliged to modify this model. And we did this in this paper here, okay? And in this paper, we introduced one displacement, always an homogenized model, but one displacement for the upper array of beams and another displacement for the lower array of beams. And we introduced an elastic energy describing the behavior of one pivot, okay? So either we have a one field model or you have a two fields model. In the one field model, you can describe only this rupture phenomenon, which is related to an elongation of one beam. So you have a kinematical descriptor for this elongation. Instead, if you have a one field model, you can never describe these other mechanisms, two other mechanisms ruptures, which occur in some pantographs with some microstructures, okay? So what we did, using the pictures we have about one pivot, we imagined a deformation energy. So together with elongation modulus, bending modulus, pivot torsion modulus, which at macro level becomes shear deformation, we invented an interaction modulus, and we added in the energy the distance between the placement of the upper layer of beams minus the placement of the lower array of beams times this stiffness. This is the standard stiffness of a spring, okay? And using this energy, we could prove that the concentration of deformation energy in the pivots are either here, so causing this rupture, which we have described there, or here, so causing the rupture, which is described there. So, standard continuum models are not good for describing these systems with a continuum model. We used a second gradient continuum model, so a model where second gradient of displacement appears. Actually, we invented this microstructure for finding this kind of microstructure. Then this phenomenology urged us to develop a two-field model, and using this two-field model, we did manage to describe also this rupture phenomenology. Okay, now I can tell you what we have done for optimizing the pandographic structure. So what we did, we said every dot represents a pivot. Every number here represents its stiffness, shear at macro level, torsional at micro level, okay? And we optimized this specimen choosing the correct stiffnesses in order to have the rupture here the latest possible. So we found the distribution of torsional stiffnesses of the pivot such that the elongation was minimal, the elongation of each of these bars all along the structure. In this way, with this distribution of stiffnesses, we can increase of another 20% the maximum elongation before rupture. So we can enlarge the elasticity domain of this new metamaterial, okay? Okay, now another question, I have 7 slides before ending. One could ask me, why you studied continuum models for these structures? The question is that we can have meso models introducing beams or micro models describing every beam at micro level, so at the level of the grains, okay, using a standard 3D continuum model. Okay, using Euler-Bernoulli nonlinear beam-based meso model, we needed 3 hours for doing this numerical simulation. Using the micro model for Cauchy continua, we needed 3 days. It was 4 million degrees of freedom numerical simulations, and we have a rather good computer which costed us 12,000 euros. So we needed a lot of time for getting this prediction in nonlinear regime. If instead you use second gradient homogenized continuum model, you need 3 minutes. Now, if you want to find this optimized scheme, you need to solve the elasticity equilibrium problem several millions times. So if you have that each simulation lasts 3 hours, you are lost. You cannot find the optimized structure. If you have 3 minutes, this is feasible, and we did this. Okay, now I want to give some hints about what we have done with image analysis for checking the quality of our theoretical models. Now, also in image analysis, you can have different layers, different length scales in analysis. If you study at this length scale, you can use a mesh which is like that in the digital image correlation scheme. If you want to use a meso model, then the mesh is this one, which finds every beam with a small number of, you see here you have something like fundamentally 3 finite elements. If instead you want to get information about what is happening at the grain scale, then you have a further detailed mesh, okay, also in the digital image correlation. Okay, in the École Normale Supérieure de Cachin, now it is Paris-Saclay, we did tomographies of these specimens, and this length scale could also be reached. Okay, now what is very interesting is that using digital image correlation, you need to tell to the numerical scheme elaborating images where it has to find a certain part of your structure. Because in large deformations, it is not obvious. Imagine the poor software, how it can understand that this cross is here and it is not that one in the actual picture. So, and I'm very proud to be co-author of such a paper with whose main idea was by Francois. In the digital image correlation scheme, he used the theory. So what he did, he said to the software, go and look for the speckled pattern in the reference configuration, deformed in this way, in this place, and try to find it. And this place and the speckled deformed were calculated using the mathematical model which we gave him. Okay, so digital image correlation is driven by the theory, as everybody knows very well if he studied a little bit of philosophy of science. Okay, we did also in Stockholm some experiments in the dynamics of these specimens. Okay, but I'm rather late. I will tell you that we got a very nice, very nice agreement between our theory and measurements. I show you some pictures of tomographic pictures made in Fraunhofer and in Kashan, who describes you in greater detail how the specimens are made. I said you digital image correlation, different meshes. So you have different meshes and different analysis at different length scales with different models used for following the deformation patterns. Okay. So this is what was called backtracking procedure. So actually, you know where you are looking for a certain deformation pattern, and then you go and find it where you predicted it should be. Okay, and you get this digital image correlation using Continuum model, and this digital image correlation using the meso model coupled with meso digital image correlations. So at the end, I am only a little bit late, at the end of the story, which is the lecture which we should learn. You have this system, okay? Forget that I invented it because I needed a second gradient material. This system is existing. So how do you want to model it? If you are happy to average what happens in this square of 5 millimeters side, then you can model this with a second gradient continuum. Of course, the second gradient continuum is not telling you in detail what happens at 1 millimeter length scale, okay? It gives you only an average deformation, which is the advantage of second gradient continuum theory. You can get quick numerical simulations, and therefore you can do optimization, okay? On the other hand, maybe you are interested in what happens to one beam. So you use a meso theory, a theory in which you have a set of beams interconnected by pivots. Okay, and you get longer numerical simulations. If by chance you are interested in what happens at the grain level of this polymer, which constitutes this specimen, then you need Cauchy theory, standard three-dimensional continuum mechanics in which the deformation energy depends only on the gradient of displacement. But you need days of numerical simulations. Finally, if you are crazy, or if you have any need to go to microns, nanometers, you will need more and more sophisticated models. So which is the message? There is no true model for this system or any physical system. It depends on the phenomena in which you are interested. At the macro level, at the level of engineers, mechanical engineers, second gradient continuum models is very efficient. Okay, this is the message. And therefore, continuum mechanics has to be studied in a more general way. So in a sense, this is an experimental motivation telling you why some theories needs to be studied. Okay, and I stop hoping that you will ask me questions showing that you liked what I said.
Thank you very much, Professor dell'Isola. It's a very informative presentation for all of us. So now the floor is for the questions. If audience, you have any questions, please ask directly by unmuting yourself, or you can write your question onto the chat box so that I can read it aloud.
Okay. So I wait for questions.
Sure. Don't need to be shy to ask the question. Maybe if you want, I can ask one question. So related to the modeling, especially for this problem,
Yes.
macro scale, like 5 millimeter, for example.
Yes.
You are mentioning about second gradient theory.
Yes.
But at this stage of the numerical solution, you are not solving it in the strong form, I guess, right? You are employing some numerical model.
We are. Look, this is a very, important question, and we go back to the first page, or maybe this one. So what we are doing, this is a typical second gradient energy. We simply give to COMSOL this energy, then it uses a minimization scheme for finding the equilibrium shapes of the specimen. So we don't talk about strong equilibrium conditions and anything like that, which, by the way, numerically are very difficult to handle. So actually, we start from the weak formulation.
I see.
And I don't know if you know, I'm not selling COMSOL, Adnan, but I must tell you that COMSOL was written by clever scientists who became rich because of it, but this is not bad. And so COMSOL has been written by somebody who knows what the code is doing. And so it is very clear for somebody who knows continuum mechanics, and it is fully based on weak formulations.
I see. And you employ always finite element method to solve it, I guess, right? As you are using COMSOL.
Yes, we use various versions of finite element methods, because as second derivatives appears, then you need higher order polynomials for handling it. And sometimes we used a mixed Reisner-Midlin integration scheme with some Lagrange multipliers in order to get a quicker time of integration. So all this, my dear friend, is hidden. I agree with you, is hidden in my presentation, but
you know, the reason I ask this question is because you are talking about a high order displacement and you need a high order derivatives. If you need a high order derivatives, you need high order shape function to solve it. What if you use for other approaches, for example, isogeometric analysis, B-splines and things like that, to be able to solve it even more efficiently without making mesh on it, you know?
Indeed, in M&MoCS group, there are at least 2 subgroups, one headed by Emilio Turco and Antonio Cazzani in Sardinia, and the other one by Massimo Cuomo in Catania, and they used isogeometric integration schemes for getting the solutions. But I don't see a big advantage. I mean, instead of 3 minutes, they needed 2 minutes, 1 minute. Okay, so we didn't have this big advantage. But of course, it could be that they didn't find the right isogeometric approximants. So I don't want to judge this in the sense that everybody who wants to use isogeometric analysis for this is welcome, and we will help him, giving him all details he needs for doing this.
I have a second question. You know, it's interesting work, to be honest. It is related to the, you know, taking things from the micro scale maybe and putting it at the macro scale and solving it as a continuum model rather than like a discrete beam model. Because I think what you are doing in the macro model is like discrete beams. You connect them with the pivots. Let's say that we want to model this as a surface element, like plane problem, you know, and we find homogenized properties of each cell, like considering that it's a repeating unit cell, you know.
This is what we did in Pandographic second gradient plate. We called it.
I see.
We called it Pandographic sheet.
So
so the macro level is with Pandographic sheets, and finite elements are those which you are telling us. Okay.
I see.
Then you have the level of mesomodel, the mesomodel, which is made of beams like that. Okay. And then you have the micromodel, which is not described in these pictures, where you zoom in at this.
I understand that part. Yes.
You zoom in at this, but it is a nightmare which was done in my group, and we needed days after having optimized. The first numerical simulations required weeks, and you cannot rely on numerical simulation lasting weeks. Then we managed to do, but you know, it was very important. I tell you, okay, as you are asking, I tell you this, I'm happy. You know, when you use a macro plate-like model like this, okay, you have a big problem. What is KE, KB, KP, and gamma, for instance?
Yeah.
Okay. So at the beginning, we made a best fitting. So we made experiments and we fitted these parameters in order to get the results. Okay. Now, this fitting is very good. Why? Because when you make shear tests, okay, like this one, when you make shear tests, where it is? When you make shear tests like this, like this one, using the parameters which you fitted in these, you get the right results.
I see.
So you are rather happy about this fitting. However, Ivan Giorgio, who is now associate professor in L'Aquila, did what we have called a numerical identification. So he made many numerical simulations using a 3D continuum model, and many simulations using the second gradient continuum model, which I show you at the beginning. Okay, so he identified these coefficients, making numerical simulations at micro level using a 3D continuum. Okay. And then, don't pull our leg, but this happened. Then we discovered that Seven identification, which is given here, which is given, let me see, with the case here. This is an identification where you have the distance between the pivots, the Young modulus, and the area of the beams, the moment of inertia of beams, and this is a standard solution for torsion of beams. Okay, we discovered that the order of magnitude given here is more or less good for this identification. Okay, because this pivot is not a beam, but it behaves in a way similar to a beam. Okay, so we have answered partially to your question. Okay.
Yes, sure. But you know, there is always something missing in the science, especially when there is a damage.
Okay.
You know,
Look,
like these parameters should be updated in a sense that, okay, there may be some plastic zone, there may be some fracture at some point, they need to be updated, you know. But for, I think, linear elastic region, it seems it's matching well.
I agree fully. And in M&MoCS group, there is also somebody studying using the methods of Marigot, studying damage of second gradient materials. So we are trying to get yield criteria using a variational principle of the kind of the one used by Marigot. Okay. So there is a lot of space left, for sure. I agree with you. And I hope that students who are hearing us now will be interested in our possible exchange program so that we can have many joint PhD students doing these kind of things. This is, Adnan, my true motivation for this kind of meetings, right?
Sure, for sure, for sure. Thank you very much for your answer. It's beautiful. There is a question from audience. Raul asked the question, can this method be effective on generation times, on new generation tires?
I mean, this is a dream, but by the way, do you have seen the new tire used for the Mars lander?
I actually seen some photo myself. I think probably Raul knows that as well.
Yeah, and it is very impressive how similar this tire is to
the
our
lattice,
Pandographic structure.
Right.
However, consider that they glue. So the angle between the beams of that tire
fixed
remains pi/2, and the deformation is concentrated between two clamping crosses.
They behave rather like a truss, I guess, right? Instead of
exactly
like truss.
Like truss. So I think that the tire of NASA for Mars lander could be improved, allowing this change of angle with an elastic element. Okay, but you know, I've seen it recently. So the question was raised by somebody with whom I would like to talk. Okay, so he can contact me if he likes via Skype or via mail.
I guess Raul hears you well. Probably he will do that. Any other question from the audience? Okay. Professor dell'Isola, it seems there is no other questions coming up.
Okay. Okay.
But thank you very much, for this very informative presentation. It was the first time for me to really see this kind of metamaterials. I think I now have a better understanding of, like its physics and its idea and invention. It's great, and congratulations on that. Really, it's very.
Thanks a lot.
Invention.
Look, we have an appointment next Monday, right?
Yes, sure.
Okay.
Sure.
Thanks
Then
a
I
lot.
will-
Thanks to everybody for patience and attention.
Thank you very
Bye-bye.
much.
Thank you.
Have a nice day. Bye-bye.
Thank you.
Bye.
Thank you.
Bye-bye.